Thank you, everyone, for having me. I'm so thrilled to be able to meet up with you all and talk to you. Today, I'm going to be giving a talk called Designing Interactive Partners for Proof. And I'm going to start with just some things that I anticipate we will all agree on, especially after seeing George's talk, which is that there have been some truly impressive formalization efforts that have shown the capacity of modern proof assistants to develop substantial systems and help us with confidence that their most important properties are upheld. And I think we'll also agree that the work involved is often immense. It involves tons of lines of proof, lots of time, lots of expertise and large teams. And even if you're not working on the four-color theorem or,
Yes, we need to share the screen.
All right, good. OK, great. All right, so lots of work to do proof, and even if you're not working on a colossal scale proof and you're just doing a smaller development, I think a lot of us can still see a lot of time and effort involved in proof work. Now, part of the solution to facilitating proof is going to be better processes, and part of it is also going to involve better tools. And it's in the space around better tools and their interface with process, as we currently understand it, that I want to share some ideas for what we can do today. So what you'll see in this talk is some of my group's efforts to make sense of this space. It will include a model of the user experience of modern proof assistants, a vision of tooling for making our notation more expressive on the written proof page, and then a vision of tooling that improves assurance through property-based testing. Along the way, I'll be trying to bring my HCI background to bear with plenty of ideas for how to structure evolution of the tooling in a user-centered way. And I'm not a programming languages or a mathematics researcher myself, but rather I'm a human-computer interaction researcher. And so in a group like mine, our work focuses first on things like articulating design parameters to guide the design of effective user interfaces, actually creating prototypes that will embody new ideas for interactive software, and then evaluating the user experience of those prototypes. You can think of us as taking a step into the future of user interfaces and figuring out whether or not that step was actually a well-made step. We leverage a good number of activities across these three stages. And so some of the more meaty pieces of our work are when we do thorough need finding before our work, when we envision and prototype novel user interface designs, and then we design studies to tease apart the impact of those user interfaces. And to just kind of set expectations here, oftentimes these are lab studies, usually pretty small scale, on the order of around 20 participants. They are rigorously designed, and they're essentially enough evidence for us to get a sense of whether our design was a hit or not and worth investing in further. And from this work, we end up, the outputs end up being research insights, which we end up publishing in top-tier HCI venues, as well as occasional PL and programming tools venues. And then occasionally tools that we can distribute. I'd say in maybe like 1 out of 5 of our projects, we have something that is actually worth making real and putting out there into the world. So the outcomes of this kind of work is a better understanding of people's work process and design primitives to support it better. Let's talk about what this looks like for proof assistants. So a lot of work in HCI is just trying to make sense of like a murky mess of expectations that we have. So where I'd like to start is just getting a sense of like what are people's expectations in this room. Maybe we can just get a few volunteers for what aspects of proof assistance do you think are usable or not. And you can just shout them out if you want to. Let's just get some ideas. Yeah, go ahead.
Often people complain about search.
OK, search is hard, sure. Others, you can just say it out loud. Yeah.
Visualizing your statements in the way you're used to.
OK, yeah, so access to visuals. Sure, love it.
Understanding when things go wrong.
Understanding when things go wrong, totally. OK, so all of us have these expectations about these challenges. We probably also have things that we love about proof assistants. To share some things that have come up in many of my prior conversations, are things like proof involves drudge work, tactics are hard to learn, if the proof checks, it's good enough, or there's more to proof than checking, it's not good enough for it to just check. Proof is a social activity. Proof is a solo activity. Real proof actually happens on paper. And so there's a lot of these expectations, and some of them actually conflict with each other. And so in human-computer interaction, sometimes we want to be able to make sense of them, which ones are actually reflective of reality, and how they all fit together. And how we did this in one of our recent studies was leveraging a method that we call contextual inquiry. And this particular method of observation involves going to the place of a person's work, watching them do their normal tasks, making hypotheses about their work in real time, and then checking these with the participants. And this method tends to be a preferred approach because of how close it gets you to real tasks and accurate interpretations. So more specifically, we called proof writers up on Zoom, and we had them work on their own proofs with their own tools. And as they did, we, the researchers, had them think aloud, where they described their work. And in the meantime, we asked them questions about what they were doing to check our interpretations. We ended up observing 30 participants from both Rocq and Lean. All of these folks had substantial experience using these tools. And they were also using them for serious developments across a large number of formalization projects. In order to analyze this data, we followed a standard qualitative analysis approach. We had 2 coders. Probably the main place that we departed is that we just had like reams of data from this, around 43 hours of session data. We transcribed it. We ended up adding in snippets of folks' proofs and also transcriptions of the actual user interface actions that they had. And then we analyzed it in kind of a standard 2 passes with occasional verification checks, validity checks throughout. Let me give you a taste of the kinds of things that we saw with a few observations. And before I do, I'll give the disclaimer that this is a collaborative project. I'm an HCI researcher. I'm working with programming languages researchers on this. This project was led by Jessica Shi. Many of the slides that you'll see here are actually her wonderful slides, and many of the slides you'll see later are from other student work as well. And so I'm going to do my best being able to channel Jessica here in some of her observations. And if you want to go more into detail on any of these observations and I'm not able to summon the details, we can definitely set up a connection. And you should also take a look at our paper. So one kind of observation was that we saw people leveraging the affordances of the proof assistant to do nonlinear proving. So for instance, we frequently saw, like in Lean, sorry tactic, in Rocq, the admit tactic, interspersed throughout people's proofs, and they essentially jumped around to the goals that they wanted to work on at that time. Not a big surprise, but we saw a lot of this. And there were different heuristics that people used in order to choose what to work on, such as the easiest goal first, or maybe the most substantial and important goal first. And they told us about how conveniently the proof assistant state helped them page back in when they were context switching from one goal to the next. Another kind of thing that we observed was people frequently stumbling around with detail work in the proof. So for instance, there's this user who had an impossible goal to prove. And this was because they lacked the fact in their environment that the length of p was 0. The user eventually found a workaround, but the easy fix that they didn't notice was this 2-character fix, that if they had slightly refined this tactic, the information they needed would have been retained in the state when they needed it. And while this specific issue didn't come up more than once, the general issue came up many, many times. And then furthermore, for many participants, proof involved continual reuse, whether it was lemma search for Rocq, Lean, referencing paper proofs, using scratch work outside the script, adapting existing proofs, copying and pasting over from them, and also adapting examples from library source code. So these are the kinds of things that we were able to see. And in fact, we observed a great richness of behaviors that fell across 4 large thematic categories. And out of all of this starts to emerge a model of proof user experience that can help us calibrate to the real work of proof. And here is how we would picture it. So in this model of the world, you start with a user and a proof. And then around this proof, you have a user interface. And as someone interacts with this proof, the proof assistant sometimes makes progress harder with some sources of undesirable work, like unforgiving tactics or unwieldy states or confusing errors. But the proof assistant also provides essential forms of support. For instance, the rapidity and malleability of feedback, a great thing, the flexibility in sequencing one's work in the way they want. And then as people adapt to the challenges and affordances of the proof assistant, they end up learning useful behaviors like becoming really good at parsing state and being able to leverage the feedback to support rapid trial and error and doing just-in-time sandboxing for experimentation. And behind all of this is the user with their goals, which importantly go beyond just achieving QED, but also includes maintainability, communication, and adhering to convention. Many of these things that we heard George talk about just a few minutes ago, we got to see those as well. And then part of the proof task involves borrowing others' work, lemmas, paper proof, and so on and so forth. And also, proof wasn't just the script. It also involved other modalities like paper and comment. So I guess the initial observation here is that this is a really rich task. And if there was any question about whether there's one dominant solution to facilitating proof, I think that they should kind of set it to rest because there are so many different pieces to this puzzle. But there sure is a lot to help with. And altogether, the observations from this study can help check our intuitions that, for instance, in many cases, people don't understand the tactics that they're using, that there certainly is drudge work, that the contents of the proof oftentimes matter, even if the script, even if it checks, and that the task is oftentimes quite solitary, but there are social elements to it. And that, of course, there's other representations that folks are working with. And the advantage of a study like this is when you go through and you read the whole paper and you see some of the numbers that we include in it as well, you start to get a sense of the prevalence of some of these tasks. So for instance, we got to see that proof involves for many people a lot of these interspersed lemma search tasks. That some of these kind of bespoke approaches, like creating these temporary environments of sandboxes, are maybe a little less common, but they are super cool. And that there's just a ton of undesirable detail work that comes up all the time of many different kinds. So given that a paper like this can be so dense with examples, let me just share a little bit with what we hope you all do with this. So I see there as kind of 5 purposes of a paper like this. For those who don't know what proof assistant work looks like at all, this is a great primer. For those of you who have intuitions about what is hard in proof, our examples can help you check your intuitions. We can also help complexify your perspective, shedding some light into when something is or is not a serious problem. For many of these things, we have both sides of the coin. When someone is building a tool, you can consider many of our reports as these case studies that you could kind of flesh out into those that would end up becoming kind of your initial cases that you support in a paper. And then for our community as a whole, I think it helps generate questions to test in upcoming studies, such as, for instance, if people are really good at parsing state, what are the points at which a particular goal becomes too big for someone to mentally parse? A really interesting and difficult research question that, if we understand, can shed some really useful insight into what it means to better facilitate proof. All right, so the 10-second synopsis of this is just that this paper unpacks these phenomena of rapid iteration, undesirable detail work, continuous reuse, mixed modalities, and aspects of a proof that go beyond QED. And that final part of going beyond QED is the part that we're going to drill down into next. So math argument needs to be written well. And let's talk a little bit about some of the work that my group has been doing that relates specifically to paper proof, as we're kind of trying to expand our space of available modalities to people. And we'll be talking about tools to make math notation more expressive. The situation in which my group first explored problems around math notation was in a small study that we ran just watching people read academic texts. And we saw that among the junior researchers that we observed, there were problems reading notation, first understanding it in the first place, and then, of course, keeping everything in one's head when there's a lot of symbols and structures that are introduced that they're not familiar with. What you can see on the right here is an example of one participant who ended up making kind of a little index of their own in the margins of the paper to help facilitate their continued understanding of notation. This ended up taking us down a rabbit hole that's given us about 5 years of research opportunities. And so before I share a little bit about what we've worked on, I'd also be interested in, there's a lot of things that we can do to make notation more understandable. I'd love to just like get some ideas as we kind of collectively think through this space. So you have a crazy piece of notation. How can you make it more understandable? Yeah, go ahead.
Good indexing and be able to see what the notation refers to without having to search it for yourself, clicking or something, and you get the context.
Exactly, that's right. So have a good index of definitions. Love it. Other things?
Maybe you make it easier for people to not use notation too much. So when you work a lot with the map, you need short notation, but when you present it in a summarized way to others, you want to replace it with more explicit, more standard notation.
I love it. Yeah, so sometimes the best notation might be no notation, that if you have other ways that are more approachable of explaining it, maybe you can opt for those. Yeah, one more?
It was a variant of switching set of notations.
Okay. Yeah, that's right. Yeah, so like sometimes entire scientific fields get to advance as soon as you invent a better system of notation. So like maybe you should be switching it over to something more advantageous. I'll take one more, sure.
Sometimes consistence tends to be very aggressive in declare notation, and whenever you define an object, it aggressively uses your notation within the pointed objects. And sometimes when you write something, the way you wrote it means something, and it's kind of lost when you print it afterwards.
So are you referring to kind of like drift between notation as it appears kind of in more informal and kind of formal presentations? Okay, yeah. Yeah, so perhaps like better consistency between the different appearances of notation in the different places that we show them. These are some great ideas. And there's a lot of things that you can do here. A couple of quick visualizations I can throw up on the screen. Sorry, Carlos.
Here's one which we really feel is going to be a big problem, which is the dot notation.
Okay. Like elisions?
It's difficult to say what that actually means, but when you read it on the paper, you tend to sort of know what it means, basically.
Yeah.
And so it's hard to explain how that process works.
So by that you mean like the cases where you say like the rest is details with like a few dots and then you select it?
Like, 1, comma, 2, comma, dot, dot, dot.
Yeah.
Transforming that into an actual, mathematical thing.
Yeah.
It's not easy, but I mean that's a simple example. But you often say something or other, dot, 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 something, which means some kind of recursive sequence of something or other. But saying exactly what that means is like a big problem.
Yeah, totally. So, I think a common challenge in notation is that oftentimes it's designed for concision, and so when you leave things out, sometimes it's ambiguous what you actually intend with your elisions and your other sources of concision. Great. Okay. So there's a lot of things that you can do to just kind of provide a quick visual for some of these things. You can bring like definitions closer to the notation. One of the things we didn't talk about so much, you can use other representations also besides notation and be able to link into those sources. And there's so many different things that, one of the things that we wanted to do was just kind of articulate the design space of what people could do for notation better. And we do this all the time in HCI. I would call it like a design space articulation. And the way that we structured this activity was we did a couple of studies. First, we sampled a large number of documents that augmented their notation in interesting ways to understand it better. So we just saw what are people currently doing. And then we followed up with interviews of the authors of the documents. And I'll return to that in a second. But our sample included documents like, for instance, this one right here was an online math explainer of Fourier series. And you can see that they brought some of the definitions into the margins of expressions that went kind of at a level above the symbols, but kind of the load-bearing expressions. We looked at some of these articles that allow people to kind of like tinker with expressions. You can see this is a Distill article from AI, and it allows you to play with the graphics and kind of has bidirectional propagation of some of the interactions. And then we looked at things like this one, which is an interactive reproduction of Burns' Euclid, where you can see they actually replaced the notation with a bunch of little kind of geometric graphics, and then there's kind of linked selection between the proof and the diagram. And then the analysis was an involved process. So this one involved 2 coders. We looked at hundreds of formulas. We classified and counted augmentations. It required thousands of judgments, dozens of hours of work. This is kind of relatively standard for these kinds of content analyses. You just kind of want to get really close to them. And then this ended up yielding a design space of augmentations in 4 categories, which we described as visual notations, text styling, like coloring and spacing, annotations, and the incorporation of interactivity. And within this space, there were 16 different kinds of augmentations, and I'll highlight a few of the overarching patterns that we saw that seemed to be really important. The first is labels. It was the second most common kind that we saw in this sample. There were many rich kinds of labels, starting at kind of the very simplest textual ones, but some of them started to incorporate visuals or refer to additional notation. In some cases, a single formula might be parsed at multiple levels of meaning, and so you might actually explain it at multiple resolutions. And then in some kind of crazy cases, we saw recursive labeling, where labels actually clarified other labels. And then we also saw frequent linkages between representations. Most commonly, this manifested through the use of color in order to call out individual expressions, and then those could be related to nearby marks in other graphics. But there were other ways to do these linkages as well, such as including arrows between things and embedded visualizations and interactivity. When we talk about interactivity, there were a few different flavors of interactivity that we saw too, which include allowing people to kind of compute with formulas. And of course, this only works with certain kinds of notation expressing certain kinds of math ideas. But it was used anyway, as well as linked selections of bits of notation and other representations. So complementing this content analysis was interviews where we talked to the authors of some of these documents. And we attempted to get a better sense of what tools need to do to make more expressive creation of notation happen more often. This led to a few observations. First of all, that the current tools are clunky to use. You can imagine people working with LaTeX with lots of nested macros, or with graphical editors that don't actually understand the structure of formulas. Both of those things are are rather clunky to use. We also saw a huge reliance on LaTeX, unsurprisingly, but the preference for people, even if they were working with graphical editors, was to start with LaTeX and then to do their additional stuff on top of the typeset formulas. We also saw cross-cutting changes. By this I mean, if you choose to colorize an entire set of expressions the same way, then you kind of need ways of rapidly turning on and off particular colors and toggling them. That could be a source of tedium. And then authors also wanted more dynamic ways to present their formulas, like building them up in pieces one by one in presentations and that kind of thing. And that's motivated our work since. So here's what we've been building, and by we I mean these students. So Zed, Jeff, Eric, Zane are the lead authors on some of the tools work that I'm going to show you. Some of the slides that you can see here are also going to be Zed's. The first tool was FFL, which made it possible to specify definitions and augmentations more crisply apart from the LaTeX in a way that augmentations can also apply across a document. So it looks like this, where the meaning of this string is you want to find all instances of the symbol n and color them deep pink within your document. And what you see here is an example of a literal selector, which is just a bit of LaTeX that says when you find this symbol in LaTeX, before you render it, do this extra stuff to it. But the language also provides other accelerators, like the ability to match wildcards, as in this more succinct selector of a fraction with kind of a variable number of letters in the top and one letter in the bottom. And beyond this kind of basic syntax, we also developed yet more methods for precision selection, and a syntax that covered some of the most common kinds of static augmentations that was meant to resemble basically CSS. And then some more kind of specialized stuff that covered things like labeling formulas and background colors, which actually needed a slightly different back-end implementation behind versus how it usually works with CSS. And all of these tools ended up leveraging modern web parsers for LaTeX, which ended up providing a really nice structure for performing some of these notational transformations that were necessary to happen. I'll give you a quick intuition for how that works. So for FFL, when you start with a styling rule and a bit of LaTeX that you want to kind of like stylize, our first step is to tokenize that LaTeX source. In this case, we use the Katek open source project, which is an online LaTeX renderer that probably many of you use, even if you don't know it. It's probably imported into many of the environments that you read math in online. And so we use Katek. You can parse it into tokens. You could parse it into trees. This particular project does tokens. And then we compile this style sheet into both kind of another token sequence you can use for matching, as well as a kind of manufactured CSS class that can do the kind of visual styling later. We do the matching, and then once we find this pattern in that token sequence, we'll change that token sequence or that tree with additional metadata for rendering later. And then what that allows us to do is that when that formula goes to be rendering, that n is going to be surrounded with a special class. And then when we apply that class to it with just your typical browser-based rendering, then that n is going to show up pink. And this is an oversimplification because a bunch of additional things are needed for the labels and for composite symbols and that kind of thing, but that's the basic intuition. And we turn this into a library where you can put this into web-based editing environments where if you have your text editor with LaTeX here, you can also have like an FFL editor like this, and then you can render it here live, such that as people continue to play around with the FFL, it will also change live these kind of cross-cutting style changes like applications of colors and labels. All right. OK, so the second tool is Freeform. And it lets people augment their formulas through linked graphical edits and LaTeX manipulations, trying to address one of those other sources of tedium. So Freeform builds up a correspondence between a graphical rendering of a formula and its markup. And so what you can see is that as you select some of these expressions in the graphical rendering, it also selects the relevant bits of LaTeX in the text editor. And then once you have this mapping, it allows you to do things like allow people to directly select symbols and then express the colors not by writing the LaTeX, but instead kind of familiar menu-based augmentation. And you also create things like labels that you can see here. All the while doing all of that kind of like drudge work of handling the macros and keeping them consistent. And we do some work in the back end to make sure that people are only selecting and augmenting syntactically valid parts of that LaTeX. Because we ground those augmentations in the markup, if a person wants to also modify the LaTeX and keep those augmentations, of course, there's nothing stopping them from doing so. Freeform supports 5 different kinds of augmentations. And it doesn't output to FFL yet, but that's also an ideal target given how cluttered that LaTeX can become. Now, the third tool that we're developing is something that's like currently under active development. It's an unfinished project, but I think it's interesting still for some of these conversations. I call it executable formulas. And given that interaction has been one of these themes that's come up in some of our content analyses, we wanted to be able to allow people to play around with formulas. For instance, being able to kind of simulate their computation by editing different values and seeing how those kind of trickle down to kind of dependent values. And to also be able to link them to other representations. So what you can see here is a generated visualization, whereas you play with the points on the graph, it also changes the values of those expressions as well. And like we can even plug those values into the formula itself if we want to. The renderer that we have here permits that as well. So of course, we're also working towards being able to support these kind of networks of formulas that are interrelated and share the same expressions and can relate to more complex visualizations like this visualization that you can see that tries to kind of unpack some of the concepts of conditional probability with kind of falling balls on these sized probability platforms. Kind of the main idea in a project like this is kind of our prompt is there a way that we can allow people to write a relatively simple formula spec that ends up getting them an interactive formula? And I think that right now it's too complex, but I think some of the key elements of it is you have to specify the formula. In this case, we do LaTeX. You have to specify the variables that you want to activate. You need to be able to kind of select those within the LaTeX, and we use kind of an FFL-like selector language. You need to specify the role of these variables. Are these controlled, or are they controlling? Some different control parameters, and then you also have to specify the semantics. And the way that we're currently doing that right now is, in this case, where this one just uses some symbolic algebra. This is that line that you can see in expression is an expression that's just passed to math.js. But you can also allow people to write JavaScript functions with those semantics, or even AI generate them if there's something like a kinetic energy equation that it's seen millions of times before. And then also, there are some elements for accelerators for creating common kinds of visualizations. Create a 2D plot that can control this and link everything up. We haven't tested the executable formulas project, but we have tested FFL and freeform. And each of these tools we see as a kind of probe. We develop it, we test it, we get a sense, is this a step in the right direction? What about it is something that we should continue to use? So in a recent study that we did, we compared together an overleaf LaTeX baseline to both FFL and freeform. And the way that you can read some of these results is that, if we just look at this one column right here, in overleaf, it took people an average of 4.9 minutes to complete a simple coloring task. And it was 2.9 minutes with FFL and 1.7 minutes with freeform. So now that you kind of know how to decode this table, the gestalt of it is that some of these tools can reduce the time that it takes to augment some of these formulas, and also lead to significantly greater self-reported ease in doing them. Now, the other thing that you'll see in this table is that also, this isn't universal. There are some tasks for which LaTeX still remains good. For instance, people are really good at moving ampersands around in order to be able to manually align their formulas. And so adding an extra level of tooling between them and alignment is actually a slowdown. And so to us, this helped us understand that the role of having these multiple representations, including the ones that people are familiar with, as part of kind of holistic toolkits for making their notations more expressive. An earlier study that we had compared FFL to LaTeX, and it showed additional advantages, like the fact that the FFL was just significantly easier to read. But also, to characterize more deeply about what was working about FFL, we analyzed our observations according to this framework called the cognitive dimensions of notations. Is anyone familiar with CDN? OK, so this is kind of a big thing in HCI programming tools groups, where CDN was created around the 90s and the 2000s to encapsulate a lot of the knowledge that had come out of end-user programming and psychology of programming studies about what are the different dimensions that determine usability of programming languages. And so when you look at the cognitive dimensions of notation, they include these dimensions. Things like the error proneness of a language, or the diffuseness, how far spread apart the different constructs are that need to work together. And so what we did to try to provide some structure to understanding what was working about these different representations was, with FFL and LaTeX, we looked at some of the detailed observation notes and interviews that we did with people, and then we tried to code it according to the cognitive dimensions, which allows us to say more concrete things like FFL improved things like reducing the viscosity of getting to a solution, reducing the hard mental operations associated with dealing with LaTeX curly braces, improving progressive evaluation by allowing people kind of continual live reviewing of their results, improving closeness of mapping by using constructs that are clearer to people, and also reducing error proneness around some of the kind of syntactically unforgiving parts of the LaTeX. And at the same time, it allows us to say with a kind of a clear mindset that there were some additional setbacks around, for instance, some issues with closeness of mapping, where some specific constructs were just not working for people. Other aspects of the language were not discoverable to them. And also, there were new classes of errors introduced by new kinds of syntactic patterns. And so these are useful things for us to note. And generally, this, I present this as a good use of a really interesting HCI framework in being able to better understand the languages that we're making for these complex technical tasks. So my takeaway from this work is that We can better explain notation if we give people better access to definitions, linkages to alternative representations in interactivity. And one way that we might do so is by allowing people to continue to work in LaTeX. But also, I think that if we were to provide better languages for rules, better ways of directly interacting with that notation on the authoring side, and providing all of these together in a tightly interconnected way, then we would end up seeing greater use of these types of patterns and greater ease in being able to do so. All right. So the last chapter of this talk is about a productivity tool for proof. This was led by former PhD student Henri Goldstein. Some of these slides are his. He's also a newly mentored professor at University of Buffalo, so if you like some of this stuff, you should check out some of the work that he's getting off the ground there. And this work helps to show the number of angles that we can approach the proof problem from. So this project is about property-based testing. And if you're not familiar with property-based testing, it works kind of like this. With a typical program under test, if you have a specification of its desired behavior, one common way of testing it is through example-based unit tests. But if you want to get more rigorous than that, but not kind of all the way to a full proof, what you might do is you randomly generate a bunch of data and you throw it at the system. And this becomes property-based testing when you test a property with each invocation on a random data input and see how many of these inputs adhere to the property or not. So the issue comes when someone tries to understand whether or not their tests are actually any good. And of course, the problem here is that it involves a lot of manual inspection of individual examples to try to intuit the gestalt behind those test distributions. And in an interview study that we ran before this project with 20 experienced users of PBT, in 1/3 of our sessions, it came up from someone that they thought that they weren't thinking as hard about what they were actually testing, or they actually had not, or they thought that maybe they hadn't adequately tested their software with their generators. And so this is a place that if we want people to get better assurance that it's starting to get towards proof, we need to provide them with better ways of looking at these property-based tests. So we developed a tool, and the way that this tool ends up coming up is that someone would be working on a property-based test like what you can see right here. So that line right there defines the data generators. That line right there defines the property, which is specified as an assert statement. And it's asserting the correct behavior of an insert operation on red-black trees. And the typical way that someone would end up testing this with PBT would be running a command line command. But the unique part that we provide is this view that then appears within someone's editor. And this view already starts to answer some of these questions about, are my tests any good? First of all, they help summarize which of your tests passed. Those are good. Which of them failed? That's something to look at. How many of them are duplicates? That's wasted testing time. But it also allows you to drill down even further. So for instance, as you go kind of down within the views, you can start to see some of these views of the examples that were actually produced. These are trees, and what you would end up noticing is that most of the generated trees are of 0 depth, which means that they aren't very useful for assessing whether or not this insert operation is doing what it should. You need some more substantial ones. So this was developed as a live tool, such that as someone goes back and they edit some of their generators or edit other aspects of their test, that then the output's going to update live so that someone can really rapidly check whether or not they're actually making progress on getting a better test distribution. So for instance, this person could now be able to see that with that simple change that they introduced, now they're producing a lot fewer very kind of trivial trees and a lot more complex ones. In other words, they now have much better assurance that their insert operation is actually doing what it should. And to just provide like a little bit of proof about the fact that like these kinds of simple changes in a user's environment can have an important impact, I'll share with you some results from a study that we ran where we had 40 participants look at Tyche's visualizations, 40 at kind of the default style of output. And what we had them do was when we showed them test distributions, sets of examples, we would show them with one of the views or the other. We would say, rank these in terms of which ones you actually think are going to find more bugs. And then we compared their ranking to an actual ranking of these distributions' ability to find bugs, as we had introduced into them through a mutation testing framework. And the short of it is that we saw significantly more correct rankings of those test distributions with this like comparatively, relatively simple intervention within their environment. We also saw that like the typical participant had 0 errors in their ranking when they were doing it with Tyche. All right. And when we started having people use Tyche, taking Tyche for a spin in the real world, we also noticed something lovely, which is that they started noticing problems in the PBT framework itself and its generator approaches. And so this additional visibility helped us find and fix 4 bugs in one of the leading PBT frameworks, suggesting the value of providing this visibility to people. Okay, so if I had more time, I would tell you a lot more about all of these projects. But just kind of wrapping this up, I hope what my hope was for this talk is that it ends up providing people more material for thinking about how to assist proof, where one of those first kinds of material is evidence of proof process with this model of proof user experience, as well as a case library for the different types of tasks that we're trying to improve. The second is a kind of material for explaining notations with this design space of different ways that we might explain it, and what I hope are the seeds of our kind of future tools for being able to explain notations. And then the third kind of material are comprehension aids, like for instance, getting assurance through property-based testing. And if you really like thinking about comprehension aids, I'll just make a quick plug here, which is that you should check out some of our other work on, for instance, program question answering, as well as text comprehension, which we've explored in my kind of broader group, many of which these techniques could apply to proof as well. But now that we have these materials, what can we do with them? Let's just think a little bit into the future. Going in backwards order, we can continue to improve approximate assurance. So if you go to Henri's prior paper, Property-Based Testing in Practice, you can find that there's a lot of need to be able to help generate data that reflects complex preconditions, with interesting distributions, with more informative shrunk-down examples, and also provide more support for more complex properties. These are all things that we can do as a community. Thinking about written math proof, we should be connecting our math representations together when it is advantageous. And one of the things that I want to point out is that it feels like this is a time when there is growing momentum for DSLs for math representation. Drawing from my field, HCI, there's been a few influential works that have tried to help people with the generation of math diagrams and science diagrams and computer science diagrams that have really lovely outputs and more usable interfaces to them. And we should be thinking about, like, especially now that we have AIs that are oftentimes getting really good at generating DSLs, maybe we can incorporate these in more ways into our writings in appropriate places. Of course, one of the things that we should also do is that given that many of our studies of these representations have been primarily with novices in the literature, because we have a chance to roll these out more to experts, I think that we just need more studies of the appropriate places to deploy them for experts. We need to expand our theory of proof user experience. The model that I presented before critically leaves out, for instance, the effort involved in specification. And of course, the effort involved includes conceptualization of specs, writing them down, reading them, and of course the fact that, like, you're never working with just one specification, but like huge sets of specifications when you have your high-level theorems and you've got your complex graphs of lemmas across these massive developments. So we need additional studies that characterize that work, and we also need a better understanding of the process of proof on paper. And one additional quick plug here is that if you're interested in thinking about proof on paper, you should also keep an eye out for some invitations that might come to some Zulips and mailing lists near you as Jessica embarks on her next project. It's kind of imminent that she's going to be disseminating amongst some of the groups here some invitations to participate and help us understand this. And then one last direction is kind of looping back to what I understand to be the goals of the Malinka project. I know I'll learn more about this over the course of the day. Though, as I understand the sketch of this project, presumably the idea is, to some order of approximation, if people write natural language specifications, they work with a tool to generate some proof. And of course, today, because like our AIs are not good enough to generate massive proofs for really hard theorems right now, it's probably going to involve decomposing it, maybe leaving out some of the work initially, which a person can then review bits of it and help it kind of like recurse into subsequently more refined details of the proof and hopefully end up at a fully proved thing. And I think the thing that I just want to highlight is that if you're doing something that follows this general structure, one of the things that we need to think about is that when you have how much of a proof is going to get refined automatically in one of these steps, there's kind of this amount that a mathematician could presumably wrap their head around. And then when you think about what an AI might do, it could either produce a refinement that's so small as to be frustrating to a user, or so big as to be befuddling to them. And so like, I think one of the overall challenges that like, we should all be thinking about is how to make sure that like, that step size is kind of resonant with that kind that a mathematician would wrap their heads around. And while I don't know how to build such a system, I certainly know how to evaluate whether a system like that is working, and it could be a really rich area for conversation. OK, and now I'd like to thank you for all of your attention and contributions, and I'd be happy to welcome some discussion.
So, are there questions to our group?
Thank you, Professor Bro. Thank you. I would like to present it. I see different methodology, and I would like to understand how you articulate them. For instance, in the first part of the talk, you were talking about interviews you did with in practice sessions of people. And at this point, I wonder whether this will lead to only small step of change in the tools, because you are always limited to what you are actually doing in your imagination. And then at the end of the talk, you were talking to something I find very different, in which you were really thinking about another kind of interface to interact with the tool you have. So how do you articulate this different methodology to evaluate your work?
Could you say that question one more time?
So it's just that at the very beginning of the talk, I feel that you were aiming for very small steps in the changes of the interface. And at the end of the talk, you were, I feel you were taking like a step away from what is currently existing and trying to change completely what you have. And so the methodology you have was completely different from the first one. So how do you articulate this line of work to be able to evaluate what you have? Because it's a very different way of working, I think.
Yeah, okay. So if I might paraphrase, there's kind of two versions of the visions in the talk. Some of these are kind of like little incremental bits of understanding what currently is, and then some of them are kind of like extrapolating big steps into the future. And so how do we reconcile those? In human-computer interaction, that's not like so much of a problem, because I think we oftentimes see ourselves as doing both at once. Oftentimes we're trying to understand what is working and what is not working about what folks currently have, because our best read on tools is the ways that people actually behave. But at the same time, HCI includes folks like Douglas Engelbart, Alan Kay, folks who were thinking about personal computing back in the 60s, 70s, and 80s, and building a bunch of hacky things that were trying to do things like way far away from us at that time. And so I guess like I guess the way that I look at this is that like I think the healthy diet of a research group is to do like a little bit of stuff that is kind of grounded in reality, and also a bunch of stuff that is kind of like aspirational that you're not sure if it's going to pan out, and your hope is that occasionally you hit with some of the aspirational stuff. And so that's how I kind of mentally fit this stuff together. One additional note that I'll add that I think helps kind of gel this stuff together is that like there's some things with current proof assistants that like even if like for instance the proof assistants that we used 5 or 10 years from now didn't look like the ones that we have right now syntactically, I think there's also some of those patterns that we would want to carry over. So for instance, like one of the major things that we talk about in the paper is all of the like nice iterative loops that the proof assistant enables, and being able to decompose the work and providing people super actionable feedback constantly that is continually reshaping their chart through the space. And so even if the tools end up changing greatly, there are some of those kind of larger shape aspects that you can see in some of the observations of what we have currently that I think will also, can really help us inform kind of more forward-looking stuff as well.
Hi, thanks for the great talk. I was kind of curious, so in the second part of your talk on notations, you were working with the base description data was basically LaTeX, which is a very, very syntactic description of like what the formula looks like, but it has no idea what the semantics of the math is. And the sort of text that we have in proof assistance has a lot more of that semantic types. We have theorems lying around, we have a lot of that information that the proof assistant is built to reconstruct. I mean, like that was the sort of things that George talked about in his talk. And so I was wondering whether, like the same sort of tools, but working with like source code that is not LaTeX code, but proof assistant code, like how that would look like, and whether there's like a lot of more things you could say, like oh, color or natural numbers blue, for instance, something you can do in proof assistant that you can't do with LaTeX code, or like what are the possibilities there, and whether it's an interesting thing to look at.
Yeah, totally. So one of the things that I think is super cool is that like in the programming languages community, we now have like a large enough body of documents where we actually have both representations that it feels interesting to think about, could you bridge them? So for instance, I think it's around like 20 to 25% of POPL papers in 2020 had an accompanying mechanized proof with them. So I think that's a great question. I think it's a really fertile area for exploration. Yeah, it would be really cool. We haven't done anything specifically in that space, but I think there's a lot of ripe area for that to be explored, and I hope it gets explored in the next couple of years.
I observed from all of your examples, the ones I've read about in your work, is that you're really straddling the syntax-semantics interface. All of the services you build so very convincingly on top of this are fed by semantics. The things you annotate, but you're actually leveraging syntax, right? Color all the capital N's in that formulae, right? You almost never want to do this because you're reusing N in different parts in your different documents and so on. So it seems to me that we should be more alert to the kind of crossing the syntax-semantics divide and work on semantics. You have to have enough semantics for that. There are frameworks for that have been missing here, like MathML, which comes from in content and presentation MathML, which you can actually generate variants of LaTeX that give you exactly this kind of parallel markup. And I think we should be, and generated HTML from their improvers and all of those kind of things. And I think that's where the fertile things are going to be.
Yeah, absolutely. So, Michael, I think you make a really apt point that we're straddling the syntax-semantics divide in a particular way that can lead to trouble. So I think one example that you provided that I think is really apt is that like, even if you look within a single text, the way that N is used is in many, many different ways with many different flavors. And so I think maybe an interesting kind of, one of the reasons that we arrived at this particular version of it is that a lot of our initial thinking for this has been outside of the space of people who think about notation from a semantics perspective, but rather think about it from a LaTeX syntax perspective. And so that kind of initial interface of the way that people write that LaTeX and connect to it is something that we've tried to initially pick as something that we think is going to look familiar to people. It ends up having a lot of these issues, and they certainly need to be resolved. What I would really love is if we did end up writing our notation in these semantics-rich ways, and then we can end up kind of matching on that semantics and enriching it in useful ways. Perhaps MathML is part of the solution, or Open Math, or some of these other standards. I think it's a really good place to explore, and obviously something that needs to be sorted out with this kind of stuff before it gets used in like really sophisticated documents. So yeah, excellent point, Michael.
Okay, so last question.
Thank you very much. If I understood correctly, this free form, right, that you explained was more like providing, say, symbolic formulas, or to be some natural language support, right, which is supposed to provide understanding. But then you talk this DSL for mass representation also showed some diagrammatic tools, right? And could you probably say a couple of more on this diagrammatic part? And actually, what I have some personal is how this natural language and diagrams, right, how they interact, just say practically, because we really have practical experience in this. Yeah.
Yeah, sure. Right. So can I paraphrase the question real quick? So can I just, is the question if I can just share a little bit more detail about like what I know about diagrams of formulas as well as their connection to other types of kind of visual diagrams?
Yeah, about tools, right, which support, say, code, ideally, with diagrams, right? And actually, if you have something to say how say, understanding via diagrams interacts with understanding via natural language.
Okay. So let's see. So as I understand, the purpose of a diagram is, there are two mechanisms that I think help with understanding in a diagram. The first is helping to pick apart what the actual conceptual pieces are of a formula. You know, kind of classically, we've got limited amount of working memory, and so if we can break it into chunks that people can reason about, then they're more likely to be able to fit it in their heads. And so presumably you want to diagram a formula at a level of resolution that both conveys the kind of meaning-bearing parts that you want, while keeping them few enough that people can keep them in their heads. And then the place where the labels come in is that if no one actually understands what those symbols mean, then it provides people a semantic representation that they can actually understand, that they can index into that notation and hopefully build up that bridge. So like, from what I know of cognitive science, I think it's those kind of chunking, the chunking and just kind of the labeling and alternative semantic relationships aspects that kind of explain the role that those diagrams are playing. And so like, that then suggests that some of the most important mechanisms to support is the ability to identify those chunks and then to be able to attach other kinds of meaning to them. And if there are additional shades of gray to that question, I'd be happy to continue to talk to you about it in a couple minutes.
Okay, so thank you very much, Henri, for your...
Thank you.